Hi everybody, this is Konstantin Läufer, your Loyola Comp 313-413 instructor, and today we're going to focus on event-based and concurrent programming in the context of developing Android apps using Scala. So if you look at this Trello card here on the right, that's going to be our focus for the next few weeks, and our main roadmap for the conceptual aspects of this phase of the course is going to be our CDER book chapter. That's here, and we'll focus in particular on the basic event-based user interaction section, and then we'll transition to the next section on interactive behaviors and implicit concurrency with internal timers. So the first one will be tied to the click counter example, and the second one will be tied to the stopwatch example, as well as your countdown timer project, which is shown here. So you were just doing the state diagram and then the actual coding project with the functional requirements stated here. And for specific issues related to Android Scala development, please continue to refer to these detailed notes here in the course notes, as usual. Okay. So let's get started here. So there's an introduction that sets a little bit of context here, and then we can kind of follow right into basic event-based user interaction, and I have the click counter example here on the left. So we'll assume this basic bounded counter abstraction, and here we can of course start out right with a test-driven development mindset and think about some particular tests that we design against this interface. So looking at the functional requirements for the click counter, if we think about this as kind of a hardware device, it has these buttons, and then depending on which abstract state we're in, and we can think about three abstract states here, at the minimum or at the maximum or somewhere in the middle, and these kind of map to these view states where only those input controls that make sense for a particular view state are enabled. So for example, when you're at the minimum, it makes no sense to enable a decrement button, so that one's grayed out, it's disabled. When you're in the middle, in the counting state, you can go up, down, or do a reset. And when you're in the maximum state, it makes no sense to increment further, so that capability is also disabled here. So in this app, the three view states map directly to the three abstract model states. They correspond to each other. So now the thing is to kind of get an idea of what user interaction is and how we understand it, and then ultimately implement it. And one thing we can do initially is, as we already started doing informally by looking at these view states, is to come up with an abstract model starting maybe with these three states, so either at the min or at the max or somewhere in between, which we call the counting state. And then we can kind of look at the behavior in an abstract way regardless of, let's say, the concrete kind of UI that we have. So this could be maybe a console application, or it could be an application with a graphical user interface. And what we see here is a UML state machine diagram that has these three states, but there are also these arrows among the states, and the arrows represent transitions that are usually triggered by incoming events. Okay, and if we look at this black circle, that is the initial state. So you can think about this as the state that the app is in when it powers up. So imagine this is electronics. So let's say you power it up, or you insert the battery, and it starts in this initial state. Okay. So then there's an unlabeled arrow, and this basically means from the initial state it just goes straight into the minimum state without requiring a triggering event. So it just transitions spontaneously. And now whenever we get an increment, we transition to the counting state. If there are further increments, we stay there as long as we're still away from the max. But when we're about to reach the max, then we'll make that transition to the max state. And now when we're in the max state, there are no transitions on the increment event. So maybe now we should discuss the format for these event or transition labels. So the first piece is the event. Then in the square brackets, there's a Boolean expression called the guard. And then there's a slash, and then there's what's called an action. So the action is a piece of code, typically. And any of these can be missing, so they're all optional. And as you see, from the initial state to the minimum, that's a spontaneous, unlabeled transition. So it doesn't require an event to occur. So the different pieces of the transition are considered as follows. So let's say we're in the counting state, and now now we need to figure out which transitions are currently enabled or applicable. And if counter is less than max minus 1, then this guard for this increment transition here that stays within the counting state is enabled, whereas this other one is disabled. So that helps you decide that if you're actually receiving an increment event right now, that you would be choosing this transition as opposed to that one. So usually the guards are in such a way that they're mutually exclusive. Okay, and if now the increment event occurs, let's say, suppose the max is 10 and we're at 7, so this guard evaluates to true, we're still away from the max, and now the increment says, okay, we have to take this transition, and we're at the point we're performing this transition, we're performing the action. That means now we're incrementing the counter. So now the counter is 8, and we're still within this counting state. So you can see how there's only one counting state that represents all the values between the min and the max, excluding the min and the max. So it's an abstraction of the actual data values, because if we had a different state for each different data value, there would be a lot of duplication. They would all look the same, except the guard would be slightly different. Well, there would be no need for a guard if we had a counting state for each data value between the min and the max. So that would make the model rather unwieldy, because there would be this state explosion. You would have a state for each possible data value, and this is having only one variable. And if you add more variables, you get kind of an explosion, because you'd have to multiply the number of states. So it's best usually to look for these kinds of abstractions and try to keep a balance between what you express as data values and what you express as states. So usually when the behaviors are the same or very similar so that they can be kind of parameterized by a data value, then it's a good idea to make that a single state. Okay. Okay. So the rest of this is pretty straightforward. So when you're at the max, you don't have any increment transitions. So if you get other increment events, nothing happens. And when you get a decrement event, well, you're at the max, so you unconditionally decrement and go back to the counting state. And then it's symmetric to what we had for increment. So you can continue decrementing as long as you're still away from the min and stay in the counting state, but then in the last step you would return to the min state. And again, that's controlled by this guard, whether or not you're still at least one away from the min, or more than one away from the min. And then from any state we can reset the counter value, and we could express that by having a reset transition in each state that would end at the minimum state. But we can also express this commonality by having a composite state, by saying, well, there's a common state that surrounds all actual states. So that's why there's this this state called global that composes all three other states. And there's a single transition from global to min. And this means basically that no matter what state we're in, whenever the reset event occurs, we're going to reset the counter to the min value and transition back to the admin state. Okay, so tying this back to the requirements, if we go back up here, the model is supposed to express and capture these requirements, so these abstract functional requirements. Okay. And there's not usually only one way to do that, but it's generally good to look for the most simple, straightforward model that still expresses your requirements accurately. Okay, so now the next step is really to map the abstract model in conjunction with these view states to an implementation of an Android app. All right. And let's say you have this layout, which you can create using the IDE. Then the question is, how do these view states get tied to this internal model? And here what we need to understand is that when you create things like buttons or other input controls, they become sources for things that are internally treated as events. And an event is basically, it's a communication step in which an event source invokes an event handling method on one or more, or in some cases 0 or more, listener objects. Okay, so that's how typically events are implemented in an object-oriented language. So meaning that the event source is, for now at least, a graphical widget, such as a button or a menu item or so, and the user triggers the event by interacting with this widget. And internally, unless there's anybody kind of connected to this widget, nothing will happen in terms of behavior. But the way we actually bring in the behavior is by saying, okay, well, let's attach some kind of listener object to the source. So that is really the key for bringing a user interface that's just a visual thing to life, by tying the events that this user interface is capable of producing to objects that are prepared to receive those events and act upon them. So what you see is a kind of a source and listener, or source and receiver paradigm. And the key design pattern that helps us with this is the observer pattern. That is the usual way to make this kind of thing happen. So when you look at the properties in, let's say, the IDE, so let's say here I have the click counter project loaded, and I can go to the main layout. Okay. Then here I see the equivalent of what we have here. Okay. And I can see that there are these buttons, and then there's this thing at the top. There's basically a text view, this thing right here, and then the three buttons. So we can select one of these, and the thing that the button, the affordance that the button provides, so the thing that it lets the user do is click it. So then we want to be able to specify what should happen if this button is clicked. And the way this kind of thing works in Android is very similar to the way it works in other graphical user interface frameworks such as Swing and others. So there's an on-click property here, and you can specify what should happen if this on-click event occurs, or the click event occurs, and you can basically specify the name of a method here. And I'm trying to see, right, so here we have to go in here, and these are methods, and we can go in here. Let's see. That's when we want to create a new resource. But we can enter here a name of a method in the activity with which this layout is associated. Okay, so it's associated. The link is established by method name. So if we go to label decrement, here it says onClick is tied to an onDecrement method. If we look at the reset button, it says onClick ties to the reset method, on the onReset method. So where are these methods? Well, here we have to look at the Android manifest, and the Android manifest is kind of the main descriptor of what happens when we start up this app, as we know. So it says, well, you're going to work with this package here, so blah 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 .ui, and you're going to load this main activity in this package. So it's going to be this package name .main activity. So now we have to look in main activity, that's in here, and what we see here is following the Android activity lifecycle. So it'll first invoke onCreate, then it'll invoke onStart, and then onResume, which is empty here because we don't need it. And in onCreate, it says load the main layout that we were just looking at. So that makes the layout that's specified declaratively as this XML file. Well, we're looking at it visually, right? But we could see here that it's just a simple XML file. Okay, and here you can see that these properties are set as XML attributes. It's easier to look at it in this way. Anyway, or in this way we have it side by side. So that's how the connection gets established. Okay. So what's the problem now? Well, obviously the problem is, where are the on, increment, etc. methods? They're not here. Ooh, something's weird. Well, but what we can maybe assume is, well, they must have been maybe inherited. So, and in fact, if we look here, the abstract adapter behavior is what provides them. So if we look at abstract adapter right here, and this is kind of a way to structure these Android apps that brings out quite nicely the model view adapter architectural pattern that we'll talk about shortly, in such a way that there's a nice separation of concerns between the activity class, which is responsible for the life cycle related behaviors, so that's written here in the comment, and the abstract adapter behavior, which is responsible for handling these incoming events. So take a look at these comments, which I took great care of writing in such a way that they add information and guide you through the code. Okay, and the other thing to look for in this class or trait is, well, this has a reference to a bounded counter model, and remember that has this interface. Okay, so this is basically a very simple abstraction, right? That has nothing to do with the surrounding user interface, and maintains this bounded counter data invariant and has these methods. Okay, and whenever, so the abstract adapter says, well, whenever it gets an increment event, and as a brief aside, when the event comes in, or when the event method is invoked, the argument to that event method is the event source, so that if we somehow, as we're handling this event, want more information about the event source and the current state of the event source, we can talk to that event source because we're getting a reference to it with the invocation of this method. But it's often not needed, so here we don't really need it. Here, all we care about is that it's an increment event that this method invocation represents. I would say, oh, okay, the user wants to do an increment, so our job here as the adapter component is to say, okay, well, that means we'll have to tell the model that we're incrementing. So that's what invoking the increment method on the model does. And now what we want to do is make sure that the user sees the effect of the increment. So we somehow need to initiate an update of the graphical user interface, in this case of the view aspect of that, which is kind of the output of the GUI. And the update view method is in here in the main activity, and that's because the abstract adapter is kind of independent of these specific view resources. And what we see here is to update the view, the adapter will obtain the current value of the model and display it in the view component with the ID text view value, which is this label here where the current counter value is shown. Okay. And then the other thing that we're doing as we're updating the view is enable or disable some of the buttons depending on the abstract model state. So we'll say, well, if the model is full, then we should disable the increment button, and if the model is empty, we should disable the decrement button. So that's what the update view does. Okay. So all of this is described here, and the fact that the event occurs is represented by an invocation of this listener method, and the naming convention is if the event is a click event, then the listener method is called onClick, and usually the event source is passed. That would be the view, in this case the actual button, which is a kind of view in Android. And that's what we see here. So the view class, of which button is a subclass, says, well, I come with an onClick listener interface, and I have a method that allows me to set myself as a listener to this event source. So, and if you didn't specify the onClick method here as the target for the onClick property here, by setting this to a specific method, okay, so if you didn't do this declaratively, alternatively you could set the click listener explicitly in, for example, the onCreate method. Okay. You know, after loading the view components, then you could do all of these things programmatically. And in some cases that makes more sense. But here it's easy because the user interface is static. It's declared statically, declaratively in this XML file. So we can also make these links in that same file, and it's very convenient. But anything that can be done declaratively can also be done programmatically. Okay. So then let's take a look at what happens when the user actually presses a button. So this UML sequence diagram shows that. So let's say the user presses the increment button. Then, because of the onClick attribute for the increment button being the onIncrement method in the activity instance, this first interaction occurs. Okay, so user presses button, that's the zeroth interaction, not shown here. We'll invoke onIncrement in the click counter activity, and that comes from the abstract adapter. That's the inherited behavior. So it says, okay, let's invoke increment on the model, and then let's invoke update view on ourself. That's why this sequence diagram points back to the current object. And in the implementation of that, it invokes the get method on the model to get the current value from the model, and then it does a set text on this other view component, which is basically the text view for outputting the current counter value. So, and then there's this set enabled on the increment button. So that's what happens specifically if you're in the admin state and the first increment occurs. Okay. So this shows you the entire flow of behaviors and information through the system in response to a single increment event. So you might ask, well, what happens if multiple events occur at the same time? And that is actually something that the GUI framework manages by saying, well, if it's currently busy processing an event, any other events that happen around the same time get put on a queue, like a FIFO queue, and they will just be processed in the order in which they were received. So event handling is single-threaded, and as we'll explore at some later point, this keeps the programming model simple and avoids the need to deal with complicated concurrency control techniques. Okay, so the other pieces here, there's a very simple counter trait, and then the bounded counter is a little extension of that trait. And the default bounded counter is the stateful Scala implementation, where it actually expresses this data invariant and always checks as a precondition that the data invariant holds, and maybe certain other preconditions hold, like we should never try to increment when we're already in the full state. And if these assertions fail, then an exception will occur. So you could see that in the log cat as a stack trace. Okay, so this is an attempt to have a data model that is as directly as possible an expression of the bounded counter abstraction that we have in the notes. Okay, so this is really all there is to it. And when you look at this running here, so let's see, here it is. And initially, the increment is enabled, the decrement is not enabled. The reset will always work, right? And then we can press increment, and you see how the decrement button is enabled right after the first increment. So right here it becomes enabled. And then if we get closer to the max, which in this case is 5, the decrement, the increment button is disabled. So, and that's usually a better user interface design choice than keeping an input control for a behavior that doesn't make any sense enabled and then showing an error message, right? So it's much more intuitive to say, oh, this button is grayed out, so that means I just can't do the increment in the max state, as opposed to something where it's enabled, and then when we press it, we then get an error message that we then have to acknowledge. So that's clumsy from a design point of view. Okay, so that's it, right? So there's nothing much to it. And of course, there are a few tests, and we can take a quick look at these. So they're just ordinary tests for the model. So here, using test case superclass, there's an abstract spec. This uses the fun spec style, and here it says a bunch of things that express our understanding of how this abstraction should behave. So for example, here we're testing very simple thing is, okay, initially it should be not full, and if we increment, then we should get one more than we had before the increment. So that we're taking a snapshot of the value here, and then we'll look, and then we expect one more than that value. Then this one does a loop in the test. So the idea is here, well, let's increment one by one until it tells us it's full. And if we then try to increment, it should throw this assertion error. Okay. And then there are the symmetric tests for decrement, so that we should get v minus 1 after one decrement. And then reset should work in such a way that we always get the min after we do the reset. Okay. And then at the UI level, there's an abstract functional test which expresses the same kinds of conceptual behavioral expectations. This one happens to be in more in a JUnit style. Okay. And this says, for example, if we, and this actually expresses testing at the system level, meaning functional testing, where the idea is we're expressing programmatically the fact that we're pressing buttons or looking at the display. So we can look at the displayed value, see here, down here. We're looking at the text of that label here that shows the current value, and then converting it to a number. So here we're saying, well, initially we expect that to be 0, so we expect to be looking at 0, and then we also expect to see that only the decrement button is disabled and the other two are enabled, and then we can simulate the actual click, the press of the increment button, and then we'll see that now the displayed value is 1. Okay, so that's what we expect to be looking at. So that's what these assertions express. Okay, and we can tie these abstract tests to the specific instance of our application using Roboelectric, which allows us to test Android apps outside of the emulator, which makes it much faster, and it doesn't require the emulator to be up. So here we just say, okay, let's extend the JUnit suite, so that's Scala test JUnit style, and we'll mix in the abstract functional test, and we'll have to provide the activity instance. So that one is abstract here, the activity. So we'll have to provide a concrete instance of the activity, and we need to do the lazy val so that we don't get a null pointer exception. And Roboelectric has these objects that support basically taking the activity through the required life cycle. So it says, okay, let's do the create, and then let's do a start, and then let's get the reference to the activity after having gone through these two steps in the life cycle. And then here we can now do an SBT test, and everything runs outside of the emulator. And in fact, there's another test that we haven't looked at yet. So there's this adapter specs. Okay. Which uses mocking to do something interesting. So the issue about the adapter is that it depends on a model instance. So this means to unit test the adapter, we somehow need to provide like a fake or mock instance of the dependencies. So in general, when we try to unit test a component that depends on other components, the dependencies need to be there, otherwise we get null pointer exceptions usually, or similar problems. And mocking allows you to do this in a more systematic way. So mocking, so there are these mock frameworks that allow you to create fake objects based on interfaces, and then we can kind of configure them. So we can configure the model that says, well, when someone invokes the min method, it should return the min value. This one goes up to 10. Okay. And interestingly, we can also mock the Android View class. And then we can interact with, so all of these tests kind of look the same way. This is again fun spec style. And that way it tells you this nice story here that is easy to read. Okay. And so each one is like this. So we'll exercise the subject under test, and we'll then look at the dependencies to verify that the subject under test, in this case the main activity, interacted with its dependencies as expected. So meaning it should have invoked the increment method on the model, and then it should have invoked an update method on the view. Okay. Actually, so here's the thing. This is just a trait that we created here, so a minimal view trait. So it's really not, we're not mocking the actual Android class. We're just mocking this trait. So so the Mockito framework will create a little instance, dynamically create an instance of this trait, which has an update method. And that's what we expect to be invoked. Okay. And we're actually testing the abstract adapter, not the Android activity that inherits this trait, but we have a little minimal concrete implementation of the abstract adapter trait. It has to have a model instance, and it also has to have an implementation of the update view method, and that's where it says update. It calls update on the view. So it expects, so this allows us to test the expectation that the increment method gets invoked on the model, and then the update method gets invoked on the view. So it allows us to verify that the adapter does, that this abstract adapter trait behaves correctly when extended just minimally, so that we can create the instance. All right, so to recap, we have learned various patterns here. We have seen examples. So one key example is when you look at the abstract adapter, that plays the role of an observer with respect to the view components. So the abstract adapter observes the three buttons. So it has a click event handler for each button, and you could see those here. So just for simplicity, or to avoid unnecessary complexity, these are all within one class or trait, but we could have had a separate one for each button, but that would have been, in my opinion, unnecessary complexity. And so that's the idea of the observer pattern, that the observer receives these events without, let's say, so it receives them without having to actively check with the event source. So it's like a callback. Okay, so when you hear callback or event listener, that is closely related to the observer pattern. So there are other patterns that are also related to callback, where the emphasis is different. So the command pattern is also a callback pattern, but in the observer pattern, the emphasis is on the fact that some object communicates an event or state change or some other interesting information to 0 or more observers or listeners. So the observer pattern is one. The other thing we saw is the dependency inversion principle. Okay. Let's see where that is. That's actually right here. So the fact that the view class owns the on-click listener interface is an example of the dependency inversion principle. So the view is a more general, more stable component that's independent of our application. So there's really no sensible way that that view could depend on whatever our application-specific adapter component wants to provide. So that's why it makes sense for Vue to say, well, anyone who wants to listen to me needs to use my interface. They cannot choose what the listener interface looks like. They have to use the event source provided listener interface. So that's an example of the dependency inversion principle. The other thing that we're seeing here more structurally is this application architecture. So this doesn't really fit on the screen, so let's shrink it. This is the model view adapter architectural pattern. And what you're observing, so some of you might have seen model view controller, which looks more like a triangle. You know, we'll study that sometime soon. In fact, yep, that's not coming up yet, but we'll look at it soon. So in model view controller, the model pushes state changes directly to the view, so the view observes the model. In model view adapter, the adapter acts as an adapter or mediator by sitting between the view and the model. So in this simple case, and you see how this architectural diagram also represents the information flow that we saw in the specific scenario that the sequence diagram represents. So what we see here is, to summarize, user presses button, then this event occurs, represented, this internal event represented by the dashed arrow. The adapter receives the event, so that's where the onIncrement method is invoked. Then the adapter invokes a method, so that's a solid arrow, invokes a method on the model, one or more methods, and then invokes a method on the view, or several methods. So this is consistent with the sequence diagram, and it shows this idea that all interactions between the model and the view go through the adapter. There are no direct interactions between the view and the model. Okay. And then finally, we also saw the test case superclass pattern here. So that's an XUnit pattern from the XUnit test patterns book. And the way that works is, well, if you have some kind of abstract fixture, then you can describe your tests against that abstraction, and then you can reuse this abstract set of tests, and you can apply it to different concrete subjects under test. So here we just have one, which is the default bounded counter, but if we had other bounded counter implementations, we could just have a tiny concrete test class subclass, or test case subclass for each of those. And we could reuse the abstract test code very easily. Then another design pattern that I wanted to point out that we have here is, of course, the template method here. So here's update view, we're calling that, even though here it's abstract. And then in the class that mixes in the trait, in this case main activity, we're filling in the template method. Okay. So in summary, let's see, we have these learning outcomes, and so dependency inversion principle, model view adapter, observer pattern, of course, event, and then the separation of, this is more of an Android technique, of separating the activity into the event handling concerns, which is the abstract adapter, and then the lifecycle management concerns, which is the main activity that mixes in the event handling from the abstract adapter. And then we saw a few testing patterns and techniques, including mocking, as well as this out of container, meaning out of emulator functional testing using Roboelectric. Okay, so this is it for now, and there will be a separate video where we go to the next step, which is internal timers, as you can, as exemplified by the stopwatch example and your countdown timer project. Okay, so this is it for now, and until next time.